Introducing Voltrac, a tractor powered by nuclear or renewable energy which is very energy efficient, has low maintenance needs and is more suitable for driverless operation using remote monitoring and several tractors by one operator. The present methods of tilling the soil and carrying out other field work by fossil fuel powered tractors has evolved over the past 80 years. Tractors have grown in size, but the basic design has not changed much. Tractors are expensive to buy and operate, are often unreliable and require a skilled driver. However, the biggest problem is that in common with road vehicles, they are powered by a finite resource, liquid fossil fuel, that is bound to become scarce at some time either through depletion or geopolitical events. They also emit large amounts of CO2, contributing to climate change. The present world population of 6.8 billion is sustained by a farming system that is nothing more than a way to convert fossil energy into a much smaller amount of food energy. This has worked well while fossil energy has been cheap and plentiful, but will fail when it becomes scarce and expensive. The frightening truth is that if we are unable to develop a farming system powered by renewable or nuclear energy, there is bound to come a time when the world population will fall. Biodiesel is postulated as an interim solution, but currently its production requires some fossil fuel input. Until its production can become fossil fuel free, it's only a halfway house solution. In addition, most production methods take up land and so reduce production capacity. A truly sustainable farming system will need to be powered by nuclear or by the sun via wind, solar, hydro, or the production of biogas. All of these are best delivered in the form of electricity. The problem is how to transmit that electricity to the farm machines at lowest cost and with minimal energy loss. The Voltrac system solves that problem. Road vehicle makers are trying to develop electric vehicles with batteries that are charged overnight or at recharge points from grid electricity. The problem they have to overcome is providing sufficient range or keeping costs and weight down. The use of electricity stored by batteries is far more efficient than using electricity to produce hydrogen, then compressing, transporting and storing the hydrogen in high-pressure tanks and then converting it back into electricity using fuel cells. For farm tractors, weight is not a big problem, as a certain amount of weight is needed to aid traction, so that 2 to 3 tons of battery pack, in place of the engine and fuel tank, would be no problem on a medium-sized tractor, but a battery to power the tractor for a full day of hard work would be very big and expensive. Also, a high depth of discharge is bad for battery life. The Voltrac system uses the existing rural electricity infrastructure or purpose-built power lines serving several farms or an entire district. The basic system has power connection points or sockets at strategic places leading from the power line. The battery charger unit is mounted on a trailer which would also carry spare battery packs, and this trailer is moved to the part of the farm where the field work is being done and plugged into the most convenient socket. When the tractor battery is at the optimum level of discharge, the tractor goes the short distance to the battery charger unit to exchange the discharged battery for a charged one. The battery exchange sequence can be automatic or controlled by the tractor driver. The exchange mechanism can be on the tractor or on the trailer. When the battery exchange means is mounted on the tractor has a small permanent battery to power the discharge mechanism and to power the tractor when moving the short distance from the discharged battery to the charged one. Electric-powered tractors would be ideal for unmanned operation using GPS guidance and remote monitoring. Machines such as harvesters could have each component driven by a separate electric motor, eliminating cumbersome power transmission drives such as shafts, belts and hydraulic hoses. This would mean that each component could have separate speed control, independent of the tractor motor speed. A fully developed, automated system would have a self-propelled battery charger vehicle. The mobile battery charging and battery exchange vehicle collects electricity from the supply line through trolley poles or a pantograph. It is propelled by electric motors and can move along parallel to the supply line. It has battery charging means and spaces to accommodate 2 or more batteries. It does not need a driver and has automatic control means so that it communicates with the tractor and moves into a position where it is available to the tractor. This system would be highly suitable for wide open areas such as the Great Plains of North America, the Eurasian steppe, the Brazilian Cerrado and the Pampas grain belt, but equally advantageous in Northern Europe and the Punjab, which has rural electricity supply for irrigation pumps. On the wide open plains, an automated version could continue working 24/7 with remote monitoring and GPS steering. No needing diesel fuel or engine servicing, it would not need to return to the farmstead. In an ideal situation of uninterrupted farmland, the tractor could work land up to 5 kilometres on both sides of the electricity supply line, so that each kilometre of supply line could service 2,500 acres of land. In practice, because of obstacles such as roads and watercourses, it would be less than this, although schemes could be set up so that one supply line could serve an entire district, with each farmer billed for the amount of electricity used.